NASA faked the moon landing. You're lying in bed, eyes closed, mind adrift. Somewhere between the hum of your ceiling fan and the memory of documentaries narrated in soothing voices, an image drifts into your imagination. A studio set, an astronaut in bulky gear, a flag that seems to wave. You've heard it all before. That NASA faked the moon landing. In 1969, the world watched grainy footage of Neil Armstrong descending onto the surface of another world. But for decades afterward, a stubborn whisper lingered. Maybe it was all staged. Maybe it was Stanley Kubrick behind the camera. Maybe the stars are missing because they forgot to paint them in. Maybe the shadows don't line up. Maybe the whole thing was filmed in a Hollywood basement and we never left Earth at all. Your heartbeat slows. Let's unpack this quiet paranoia. First, the missing stars. The moon is incredibly bright, especially under direct sunlight, and the camera exposure was set for the surface, not the background. That's why you don't see stars, not because they were forgotten, but because the cameras couldn't catch them. Like trying to spot faint stars during a daytime photo on Earth. Then the waving flag. In the vacuum of space, it doesn't ripple like cloth in the breeze. It jiggles once, because of momentum from being planted, then stops. NASA even equipped the flag with a horizontal bar to hold it aloft so it wouldn't hang limply. The waving illusion. Just inertia, not wind. And those shadows? They're not inconsistent. They only appear that way because of the moon's uneven terrain. No atmosphere means no scattering of light, so shadows are sharp and strange. Our brains, used to earthly physics, misinterpret what they see. But what about radiation belts? Wouldn't astronauts be fried? You're thinking of the Van Allen belts, zones of charged particles trapped by Earth's magnetic field. The Apollo missions plotted a path that skirted the belts, and the astronauts passed through quickly, receiving less radiation than a modern-day chest X-ray. Still awake. The hoax theory exploded during the Cold War, when distrust in government ran high and science fiction bled into public consciousness. But there's something oddly comforting about conspiracy, isn't there? A simpler explanation than decades of math, engineering, and human courage. And yet, consider this. Over 400,000 people worked on the Apollo program. Engineers, mathematicians, technicians. People who designed rockets, tested heat shields, programmed guidance systems, built launch towers. If it was faked, not one of them ever broke silence. You drift closer to sleep. The truth is, disbelief often feels safer than wonder. It's easier to think we never went than to imagine a human being standing on a lifeless world, surrounded by silence, with the Earth hanging small and blue in the sky behind them. But we did go. Not once. 6 times. And all it takes to remember that is a quiet night, a sleepy mind, and the will to believe. Not in a camera trick, but in the astonishing reach of human hands. Now close your eyes and dream of footprints on dust that no wind can erase. The dark side of the moon is always dark. You lie still, tucked in and barely breathing as the moonlight brushes the curtains. Somewhere out there, past the clouds, the moon hangs silently in space. And you've heard the phrase before, so often it sounds like fact. The dark side of the moon. But here's the twist. There is no dark side. Your thoughts slow, drifting into orbit. It's true that one side of the moon always faces Earth. That pale, cratered face we see from our windows, from beaches at night, from telescopes and childhood books. It never changes. That's because of tidal locking. The moon spins on its axis at just the right rate to always keep one hemisphere pointed at us. It rotates once every time it orbits Earth. So yes, we only ever see one side. But darkness? That's something else. The moon is constantly lit, just like Earth, by the sun. The far side, the one we can't see, isn't shrouded in eternal shadow. It experiences day and night, just like the near side. When we have a new moon and the face turned toward us is cloaked in darkness, the far side is fully lit. It's basking in sunlight while we look up at a blank sky. So where did this myth come from? Blame the language. Dark doesn't always mean shadowed. Sometimes it means unknown. Before 1959, when the Soviet Luna 3 spacecraft sent back the first images of the far side, no human had ever seen it. For centuries it was hidden, mysterious, unexplored. Dark became shorthand for unseen, but now we know. The far side is rugged, battered by more craters. It lacks the big smooth plains, the Maria, that make the near side look like a face. It's rougher, colder, more dramatic. And during the lunar day, it glows just as bright. When the sunlight sweeps across it, those jagged mountains shine like silver blades. Still awake? Let your mind drift to Apollo 8, 1968. The first humans to orbit the moon. As their spacecraft slipped around the far side, radio contact with Earth was lost. Briefly, completely. Silence, blackness, and then, on the return, they saw it. Earthrise, our planet rising like a blue marble over the edge of the lunar horizon. Not a myth, not a trick. A real moment, captured forever. A moment that shattered the idea of darkness in space. So next time someone mentions the dark side of the moon, you'll know better. It's not a shadowed realm of secrets, it's just the far side. Lit half the time, silent all the time, and now mapped in stunning detail. And you're floating now in your mind's orbit. Slow, silent, peaceful. The moon turns slowly beneath you, never revealing more than it must. But now you know the truth. Darkness, it turns out, is just what we haven't looked at yet. Humans explode into space without a suit. You hold your breath, imagining it. A lone astronaut drifting in the void. Something goes wrong. A hose snaps. A suit tears. In an instant. His body swells, his eyes bulge, his blood boils. And then, boom. He explodes. At least, that's what the movies told you. But let's step outside the cinema. Step into the silence of real space. And look closer. First, no, you won't explode. You are not a balloon. And space isn't a Hollywood blender. Your skin is surprisingly strong. It's built to hold you together, even when pressure vanishes around you. That doesn't mean you'll be fine, but it's not a fireworks show. Let's walk through it. Say you suddenly find yourself exposed to the vacuum of space. No suit, no helmet, just you and the cosmos. First, the air in your lungs rushes out. Not because you're breathing, but because there's no pressure to hold it in. Try to hold your breath, bad idea. Your lungs could rupture. So your chest collapses. Not with violence. Just a terrible, breathless silence. Then, the moisture on your tongue and eyes begins to boil. Not from heat, but from physics. In a vacuum, liquid boils at much lower temperatures. Saliva bubbles. Tears evaporate. Your skin feels cool, dry, wrong. You won't freeze, not immediately. Space is cold, yes, but heat doesn't vanish all at once. There's no air to carry it away quickly. So you'll feel strange warmth lingering on your face, even as your blood begins to lose oxygen. Within 15 seconds, you're unconscious. The brain, deprived of oxygen, shuts down. A quiet fade. A final dream. But still no explosion. Not even swelling like a balloon. Yes, your body expands, gases in your gut and blood start to bloat you, but not grotesquely, not violently. You might double in size, but your skin holds, you remain whole. And if you're rescued quickly, within about 90 seconds, there's a chance you could survive. That's not science fiction. That's NASA's research. It happened once. In 1966, a technician testing a pressure suit lost consciousness in a vacuum chamber. His last memory before blacking out? Saliva bubbling on his tongue. he lived. So why does this myth persist? Because the truth is slower, scarier, and far more intimate. Exploding is quick, clean, but space doesn't kill you with a bang. It kills you with a whisper, a breathless gasp, a boiling tear, a slow drift into black. Now you know. Next time the movies throw an astronaut into space like a water balloon, you'll remember the truth. And maybe tonight, as you close your eyes, you'll imagine yourself there, not exploding, just floating, silent, weightless, wrapped in the quiet terror of the stars. The Great Wall of China is visible from space. You're standing on the moon, looking down at Earth, blue and glowing. Your suit hums quietly. You imagine astronauts waving to the people watching from home, and someone whispers into your headset, "Look, you can even see the Great Wall of China from up here." It's one of the oldest myths in space lore. A casual fact dropped at dinner parties. A line printed in school books for decades. But here's the truth. You can't see the Great Wall of China from space. Not with the naked eye, not even from low Earth orbit. Why? Because the wall, despite its massive length, is narrow. Think of it like a pencil line etched across a football field. Long, yes, but barely wider than a highway. It blends into the landscape, the same color as the surrounding mountains and Earth. There's no stark contrast, no reflective surface to make it pop. And space, contrary to popular belief, doesn't give you supervision. Even astronauts themselves have corrected the myth. In 2003, China's first astronaut Yang Liwei went to space. Reporters eagerly asked him if he saw the wall. His answer, no. From the International Space Station, flying about 400 kilometers above the Earth, you can make out cities at night. You can see the Amazon River. Sometimes airports and roads shimmer under the right conditions. But the Great Wall, it hides in plain sight. So where did this idea come from? Centuries before spaceflight, people imagined that something as grand as the Great Wall must be visible from heaven itself. It became a symbol, not just of human achievement, but of scale. A shortcut for saying, this is enormous. And when the space age began, that story hitched a ride into orbit. A perfect myth for an age of wonder. But there's a deeper irony. You might not see the wall from orbit with your own eyes. But satellites, with powerful cameras, can, in infrared, with enhancement. It's not that the wall is invisible. It's just that your eyes, designed for forests and firelight, aren't the best tool for scanning continents. So tonight, as you drift towards sleep, picture yourself in orbit. The Earth rolls below, a swirl of blue, green, and cloud. You squint, searching for signs of humanity, and you realize the real miracles aren't what you can see, but what people believed they could see. A wall that touched the heavens, a myth that refused to die, and somewhere down there millions of lights blink quietly into the night, building toward the stories that tomorrow's astronauts will have to bust. Sleep well, explorer. Even if you can't see the wall, you're still part of something vast. Black holes suck everything like a vacuum. You drift quietly in orbit, watching a distant swirl of stars and darkness. A black hole sits on the horizon of imagination. Invisible, but terrifying. And in your mind's eye, it sucks everything like a cosmic vacuum cleaner. That's the myth, that black holes are space's version of a drain, ravenous, inescapable, and devouring everything in sight. But that's not quite how they work. You don't get pulled into a black hole just by passing nearby. In fact, if our sun were replaced by a black hole of the same mass, Earth would still orbit it. Calmly, undisturbed. There'd be no apocalypse, no spiraling death dance, just darkness, because black holes don't suck. They obey gravity, the same force that keeps you on the ground, that binds moons to planets and planets to stars. A black hole is just an object so dense with gravity so intense that not even light can escape it. But you'd have to get dangerously close, past something called the event horizon, before there's no turning back. It's not that black holes chase you. It's that if you come too close, they change the rules. Fall in, and time stretches. Space warps. From the outside, you seem to freeze in place. From your perspective, you fall, and never stop. But let's rewind. Why do we imagine them as vacuums? Maybe it's the name. Black hole sounds like a tear in the universe, like something that eats reality itself. And in science fiction, they're often shown devouring starships and solar systems with impossible hunger. A perfect villain. But in truth, they're neat, predictable. You could orbit a black hole forever if you kept your distance. Some black holes even help galaxies form by regulating star growth, like quiet cosmic architects. Others, like the supermassive one at the center of our galaxy, simply sit there. Massive, ancient, mysterious. Yes, if you cross that invisible boundary, you'd be gone. Information lost, crushed into a singularity smaller than a grain of sand. But that boundary isn't chasing you. It's waiting. And in space, most things are. So as you close your eyes tonight, let go of the myth. Black holes don't suck. They pull, like all things with gravity. They're not monsters, they're puzzles. Ancient scars left behind by stars. And somewhere, in a far-off corner of the universe, one waits patiently. Silent, still, powerful but not hungry. Sleep gently and know, even the universe's darkest places follow rules. The sun is yellow. You glance up at the sky during a warm summer evening. The sun, low on the horizon, glows a soft golden yellow, maybe even orange if you squint through the haze. You imagine it that way always, a friendly yellow ball, cheerful and warm, like every crayon drawing from childhood. But here's the myth. The sun is yellow. It's not. Stand outside Earth's atmosphere, no clouds, no air, no scattered particles, and you'll see it for what it really is, white, blinding, pure white. That's right. The sun, in space, doesn't wear the golden disguise it puts on for Earth. It shines with all visible wavelengths of light blended together. That mix, when unfiltered, creates a brilliant white, not yellow, not orange, not red. So why do you think it's yellow? Because you're seeing it through the lens of Earth's atmosphere. When sunlight passes through the thick layers of air, dust, and pollution above us, its shorter wavelengths, blue and violet, scatter in all directions. That's why the sky is blue. The remaining longer wavelengths, reds, oranges, yellows, dominate what's left of the light beam that reaches your eyes. During the day, especially near sunset, the sun appears yellowish or orange. It's just a trick, a byproduct of scattering, refraction, and human perception. But you're not entirely wrong to feel something emotional about that golden glow. The yellow sun lives in our stories, our flags, our religions. It symbolizes life and warmth and constancy. Still, scientifically, the sun is a G-type main sequence star. It's hotter than it looks, about 5,778 Kelvin at the surface. It's not even particularly yellow compared to other stars. Some are truly red, some are deep blue. Ours is average, plain white, deceptively so. And what's more, it's not on fire. That's another myth. The sun isn't burning like a campfire. There's no oxygen. And what it's doing is nuclear fusion, smashing hydrogen atoms into helium at its core. It releases an impossible amount of energy every second. It's more of a nuclear engine than a flame. It glows not from combustion but from pressure, plasma, and atomic violence. So next time you see it, remember this. The golden warmth you feel on your skin is filtered illusion. The real sun. A howling, blinding sphere of light and energy, white as snow, fierce as anything in nature. And still, it rises every morning like clockwork, a white star in yellow robes. You blink, you yawn, you let your thoughts drift. And somewhere behind your eyelids, the sun continues its silent nuclear heartbeat. Not yellow, not gentle, but constant. Mars is red all over you. Look at the pictures, satellite shots, Mars rovers, telescope images. One thing always stands out. That red. A rusty, burnt orange glow that paints the surface of Mars like a planet dipped in powdered brick. Everyone knows it as the red planet. But here's the myth: Mars is red all over. It's not. Step closer, drift lower. Not as a floating spectator, but as a ghost gliding across its terrain. The illusion begins to crack. Yes, large swaths of Mars are coated in iron oxide dust, the stuff of rust. That's what gives the planet its infamous hue. Tiny particles, finer than talcum powder, are swept up by winds and suspended in the thin atmosphere. They scatter sunlight, painting the sky in an eerie salmon pink at dusk. But Mars isn't uniformly red, not even close. You touch down near Olympus Mons, the tallest volcano in the solar system. The slopes are dark, almost charcoal gray, made of ancient basaltic rock. Elsewhere, the Valles Marineris, a canyon system that makes Earth's Grand Canyon look like a scratch, plunges into shadowy layers of ochre, bronze, and chocolate brown. You glide over polar caps glittering in white, frozen carbon dioxide and water ice. In winter, they spread farther, turning parts of Mars into a pale, ghost-like world. And under the surface, radar peaks reveal buried layers of ice, darker bedrock, and even possible underground lakes. It's not just a one-tone desert. It's a dynamic landscape, pockmarked by meteorite craters, streaked with dust devils, and layered with history. Even the skies shift. During dust storms, the entire planet can turn yellowish. On clearer days, the sky appears beige or light brown, unlike Earth's blue. Sometimes, when dusk falls, the sun actually looks blue from the Martian surface, a haunting reversal of Earth's golden sunsets. So why do we call it the red planet? Because red is what we first saw through Earth's telescopes. Red is what early astronomers scribbled into their star charts. Red is what stuck in human imagination, the color of war, of blood, of the Roman god Mars himself. The myth clung to us like dust clings to Mars's surface, but now we know better. The red planet wears many colors. Red is only its mask, the one it shows from afar. Underneath, it's a planet of surprises, of silent white poles, of deep black rock, of soft pink skies and cobalt sunsets. A place where red is merely the surface story. And in that quiet Martian twilight, as the stars rise and the winds whisper, the planet seems to sigh, relieved that someone finally noticed. You settle deeper under your blanket. Mars turns slowly beneath a distant sun, and the red fades into dreams. You float in space. Because there's no gravity. You've seen the videos. Astronauts drifting like feathers, tools hovering in midair, water forming perfect wobbling orbs that refuse to fall. The phrase repeats in documentaries and classroom lectures like a lullaby. There's no gravity in space. But that's a myth. A gentle, misleading one. Because space isn't devoid of gravity. It's a ballet of it. You close your eyes and let yourself rise. Not far. Just to low Earth orbit, a few hundred kilometers above the ground. The same place the International Space Station orbits. And you feel it. Gravity. Still there. Still pulling you downward. In fact, gravity up there is only slightly weaker than it is on Earth's surface. About 90% as strong. So why do astronauts float? Because they're not resisting gravity, they're falling with it. The station is moving forward at around 17,500 miles per hour. Fast enough that, as it falls toward Earth, The curve of the planet drops away beneath it at the exact same rate. It's like rolling a marble off a table, but the table keeps curving down and away. That's called free fall. You're falling. Everything around you is falling. But there's nothing to hit, no floor to stop you, so you drift, gently, eternally. That's weightlessness. It's not that gravity's missing, it's that everything is caught in a shared fall. A delicate, ongoing dance. Even out at the moon or around Mars, or near Saturn's icy rings, gravity is still there, tugging, guiding, cradling moons and comets and space probes like a mother's hand on a child's shoulder. Without gravity, the planets wouldn't orbit the sun. Tides wouldn't rise or fall. Stars wouldn't form. Time wouldn't bend near black holes. The universe would unravel like thread snipped at both ends. No gravity, no structure, no meaning. And yet the myth persists, because weightlessness feels like the absence of gravity. And we trust feelings more than physics. But now you know the truth. Space is full of gravity. It shapes every orbit, every eclipse, every wandering comet. And the next time you see an astronaut spinning slowly, arms out, eyes wide, you'll smile. Because they're not floating in nothing. They're dancing with gravity. And now, so are you, in the quiet pull of sleep, drifting softly like a satellite, falling forever but never landing. Let gravity carry you, don't fight it. Just close your eyes and drift. The moon has no influence on humans. You felt it. Maybe you didn't even realize it at the time, that full moon night when sleep escaped you, when people seemed restless, when the streets were just a bit louder. Strange behavior blamed always on that glowing disk in the sky. The moon has no influence on humans, they say, but something inside you doubts that. Let's drift together beneath the moonlight. Above you, a silver sphere hangs suspended. It's ancient, scarred, familiar. It pulls oceans, swells tides, whispers to wolves. Yet science, modern and sharp, insists it doesn't tug on you. You're mostly water, aren't you? The logic seems simple. The moon creates tides by pulling on Earth's oceans with gravity. But people are not oceans. We're small, contained. Surely the moon's tug is too weak to stir the water in your veins. And yet, emergency rooms report spikes in activity during full moons. Police officers swear by it. Birth rates, crime rates, even sleeplessness, all rumored to climb with the lunar cycle. Myths wrapped in anecdote, passed from generation to generation like lunar folklore. Science struggles to confirm it. No solid statistical proof, no causal link. But the mystery lingers. The moon may not control your body, but it does shape your world. No moon, no tides, no stable climate, no regular stirring of Earth's oceans to spread heat and life. Without the moon's gravitational nudge, Earth's axis would wobble wildly. Winters would freeze. Summers would burn. The planet's heartbeat would falter. And more than that, the moon gives rhythm to time itself. Months, once measured by its phases, festivals, harvests, myths. The moon lit the path long before streetlights. It guided sailors, inspired poems, marked rituals. It turned darkness into silver. Even now, it pulls at your mind, not with physics, but with feeling. You look up and sense something old watching back. Not malicious, just present, eternal. So maybe the moon doesn't drive you mad. Maybe it doesn't spark crime or birth or panic, but it does touch you in ways harder to measure. It calms, it stirs, it reminds. You are not apart from the cosmos. You are within it, tied to it. Your ancestors told stories under that same moon, danced beneath it, feared it, loved it. You breathe, and somewhere above the clouds, the moon drifts on, cold and steady. And tonight it watches over you, as it always has, so don't fear its light. Let it soothe you. Let it lull you back into the slow pull of dreams. The moon doesn't control your body. But maybe, just maybe, it still whispers to your soul. Venus is Earth's twin and habitable. You close your eyes and picture Venus. Soft clouds, golden light. A twin to Earth, they said. The planet of love, draped in beauty and mystery. So close in size, so close in orbit, surely it must be habitable. After all, it's Earth's sister, right? The myth is that Venus is a habitable twin. But peel back the clouds, and you find something very different. Venus isn't a warm spring morning. It's a pressure cooker, a furnace sealed shut. Its skies aren't clouds of mist, but acid. Sulfuric acid, the kind that burns through skin, steel, and hope. The ground, a crust of cracked rock hot enough to melt lead. You wouldn't just die there, you'd be crushed, boiled, and dissolved, all at once. Still, the myth persisted for centuries. Early telescopes saw clouds and imagined oceans. Maybe jungles, too. Science fiction writers called it a lush world, a green paradise veiled in fog. Some even imagined Venus as a prehistoric Earth, filled with dinosaurs and dense forests just waiting to be explored. But then we sent the probes. The Soviets got there first, the Venera missions. Brave machines built like tanks, each one battered, melted, silenced within minutes. They saw an orange sky. They felt a heat of 900 degrees Fahrenheit, the pressure of a kilometer-deep ocean, their circuits fried, their metal buckled, and all illusions melted with them. Venus is not a mirror of Earth, it is a warning. Its atmosphere, thick with carbon dioxide, traps heat in a runaway greenhouse effect. Once it may have had oceans, maybe even life. But something changed. The water vanished. The planet burned. Some scientists wonder, is this Earth's future? You drift with that thought, of a world that became uninhabitable not because of war or invasion, but because its own air betrayed it. So why do we still call it Earth's twin? Because size and distance aren't everything. In truth, Venus is more like Earth's shadow, not a reflection, but a dark possibility. And yet, some still dream. They talk of cloud cities floating high above the acid storms where pressure is Earth-like and the temperatures are mild. A Venus colony, not on the surface, but in the sky. Like airships adrift in a sulfurous world. Could that be humanity's second home? Perhaps. But for now, Venus remains a lesson wrapped in myth. A sister not of harmony, but of fury. The next time someone calls Venus Earth's twin, remember, beauty can deceive. And not all siblings are kind. Now let that fiery world fade from your mind. Return to Earth, cool, quiet, and alive. Astronauts can just fall back to Earth. You picture an astronaut, floating alone. Maybe they've slipped, maybe they've been knocked loose. Their tether whips behind them, useless now. They drift away, slowly spinning, Earth shrinking in the background. And someone says, don't worry, they can just fall back down. The myth is that astronauts can simply fall back to Earth, as if space is a diving board, as if gravity is a hand gently tugging, ready to pull you home. But that's not how orbit works. That's not how falling works. Here's the truth. Astronauts on the International Space Station are already falling, all the time. The only reason they don't hit Earth is because they're moving sideways so fast, they keep missing it. 17,500 miles per hour. That's not just fast, it's fast enough to circle the planet every 90 minutes. So what happens if you drift away? You don't fall down. You keep falling with Earth, only now you're no longer in sync. You might move slightly higher, slower, or spiral out. But gravity won't yank you back like a magnet. There's no sudden drop, no cartoon plummet, because in space, falling isn't falling straight, it's falling forever, sideways. Some imagine the astronaut activating thrusters, pointing themselves toward Earth and descending like a parachuter. But orbital mechanics doesn't care about direction. It cares about speed, and reducing your orbital velocity enough to re-enter the atmosphere takes planning, timing, and fuel. Lots of fuel. Think of it like this. You're on a racetrack, doing laps at blistering speed. To get off, you can't just jump. You have to slow down dramatically without spinning out. That's what re-entry really is. That's why astronauts don't carry drop buttons. That's why returning to Earth takes entire teams, calculations, heat shields, and carefully angled trajectories. One mistake, and you skip off the atmosphere like a stone on water, or burn up. This is what makes space so frightening and beautiful. You float not because there's no gravity, but because everything, you, your ship, your spoon, is in free fall. Orbit is a dance with gravity, not an escape from it. A perfect, perpetual fall around the Earth, and once you're adrift, it's not a question of falling down, but falling wrong. So the next time you watch an astronaut hover in a spacewalk, tether swaying gently, remember, they are balanced on the edge of motion and physics, not simply floating, but obeying invisible rules, written in mass and math. Fall asleep now, gently. But know that in space, falling is an art, and returning home is never just a drop away. The sun will explode. Soon, the sky glows orange, then fades to black. You glance up. The sun is gone, tucked behind the curve of the Earth, and for a moment, the world feels quiet. Then someone whispers, "You know the sun's going to explode someday, right?" Your heart catches, but is it true? The myth is that the sun will explode soon, like some ticking bomb ready to detonate in our cosmic neighborhood, vaporizing the Earth in a sudden, fiery blast. But stars, especially ones like our sun, don't go out with a bang. They fade, slowly, quietly. Their deaths are measured not in hours, but in epochs. Right now, the sun is stable, calm even. A G-type main-sequence star, middle-aged in stellar terms. It fuses hydrogen into helium in its core, a process that releases light and heat. This fusion keeps gravity from crushing the sun in on itself. But one day, the hydrogen will run low. Not soon, though. The sun has been burning for 4.6 billion years. It has enough fuel to last another 5 billion. That's billions. Not decades, not centuries. A number so vast, it curls at the edges of comprehension. When the end begins, it won't be explosive, it'll be slow. The sun will expand, swelling into a red giant. Mercury and Venus will be consumed. Earth may be scorched, may be swallowed whole, but not instantly, not violently. There will be no supernova. Our sun isn't massive enough. Instead, it will shed its outer layers gently, like a flower opening in reverse. The core, a white dwarf, will remain, glowing softly for eons before finally dimming. No mushroom clouds, no death rays, just a long, stellar sigh. So why does this myth survive? Because we fear endings we can't see. Because exploding sun sounds like a movie. Because we like drama. And because space, vast, dark, indifferent, already feels dangerous. It's easier to imagine it destroying us in a flash than to confront the truth. Most cosmic threats are slow, quiet, and patient. Even if you lived 100 lives, you'd never see the sun's final act. What you can see, though, is light that left the sun 8 minutes ago, crossing the void to kiss your skin. A reminder that our star, for all its power, is a gentle giant. A steady beacon in a turbulent universe. So next time someone says the sun might explode any minute, you can smile. Because you know the truth. You've seen through the myth. The universe is completely silent. You stare into the night sky and imagine space, not as a place, but as an idea. A black, endless void where planets drift in stillness and stars shimmer like forgotten embers, and in that vision there is no sound. They say space is silent. Utterly, perfectly silent, but that's only partially true and entirely misleading. Let's start with the science. In space, there's no air, no molecules bumping into each other to carry vibrations. So, yes, you can't scream in space, not because the cosmos doesn't care, but because there's no medium for your voice to travel through. That part's true. But silence? Not really, because space vibrates, it hums, it pulses with energy on frequencies beyond what your ears can register. Jupiter emits bursts of radio waves as if it's growling through a cosmic megaphone. The sun sings, not with chords and lyrics, but with pressure waves rippling through its plasma. Black holes, when they collide, send gravitational waves across the universe, warping space-time itself. Our instruments hear what we cannot, and when NASA translates those frequencies into audible sound, it becomes eerie music, unsettling and beautiful, like the sigh of ancient stars, the groan of a galaxy spinning on its axis, the cry of a dying sun. So is the universe silent, or are we simply deaf? In 2003, scientists detected a sound wave from a supermassive black hole in the Perseus cluster. It was the deepest note ever observed. A B-flat, 57 octaves below middle C. A frequency so low, it takes 10 million years to complete a single cycle. Imagine that. A note stretched across time itself, echoing like the heartbeat of something larger than comprehension. But we've never stopped imagining silence. Hollywood reinforces it. Starships gliding noiselessly, explosions muffled into nothing. Reality? If you were near that blast in an atmosphere, it would tear your eardrums apart. On the moon, you wouldn't hear the thud of a boot print. But if an astronaut's helmet were pressed against something, say a lunar rover, vibrations could travel through the solid structure and reach their ears. Sound still exists in space, just not in the air. It lives in radiation, in data, in interpretation. We build machines to convert invisible signals into something we can understand. And when we do, the cosmos speaks, not with words, but with the slow rumble of giants, with the shudder of stars collapsing, with the rhythmic chime of pulsars, those spinning neutron stars ticking like clockwork through the abyss. So, next time someone says space is silent, remind them. The silence isn't out there. It's inside us. We're just learning how to listen. There's no weather in space. You imagine space as a place untouched by change, a sterile void, cold and still. Earth has storms, skies that twist in fury, and oceans that rise in revolt. But space? Space is silent, still, unchanging. No clouds, no wind, no rain. So, there's no weather, right? You float just outside the atmosphere looking down at your planet. A beautiful blue swirl of life and motion, but above you, above Earth's reach, the universe brews a different kind of storm. Not made of water or wind, but of particles, radiation, and raw cosmic violence. Space has weather, and it's far more terrifying than any hurricane. It begins at the sun. That glowing sphere you take for granted, it's not a quiet light bulb in the sky. It's a boiling cauldron of nuclear fusion, flinging out solar flares and coronal mass ejections, bursts of charged particles hurled into the solar system at unimaginable speeds. When these solar eruptions hit Earth, they distort our magnetic field, spark geomagnetic storms, and trigger auroras, those glowing green veils in polar skies. They also fry satellites, disrupt GPS, and once, in 1989, blacked out the entire Canadian province of Quebec. Imagine that. The weather in space knocking out your lights at home. Then there's cosmic radiation, invisible, constant, and deadly. Not weather in the traditional sense, but a relentless storm nonetheless. On Earth, you're shielded by atmosphere and magnetosphere. But in space, astronauts are bombarded by high-energy particles from distant supernovae, gamma-ray bursts, and solar outbursts. It's not a matter of if these will hit, only when. Storms of radiation drift silently across the void. No sound, no warning. You can't hear them, but your body will. Even planetary bodies aren't immune. Mars, with its thin atmosphere, is regularly blasted by solar storms. Its weather isn't clouds and drizzle. It's dust devils spiraling across rusted plains whipped by the breath of an ancient, cold world. Jupiter's Great Red Spot. That's a storm bigger than Earth itself, raging for over 300 years. Space weather doesn't just shape planets, it erases them. In 1859, the most powerful solar storm in recorded history, the Carrington Event, struck Earth. Telegraph systems sparked into flames, auroras danced over the Caribbean. And that was before we had a planet filled with electronics and orbiting satellites. If it happened today, the damage would be measured in trillions. There's no drizzle in space, no umbrellas or thermometers. But make no mistake, the cosmos has weather. It's just invisible, silent, and waiting. And it doesn't care whether you believe in it or not. Asteroids are all gigantic death rocks. You see one in a movie, a jagged monster of stone tumbling through the void, glowing red from atmospheric friction. Sirens wail, scientists scream. The countdown begins. Asteroids, it seems, are Hollywood's favorite apocalypse. Giant space rocks just waiting to wipe out civilization. And you wonder, are they really all that dangerous? You drift out into the asteroid belt, floating between Mars and Jupiter, expecting a battlefield of colliding boulders, but instead it's quiet. Sparse. There's distance between these objects. Hundreds of thousands of kilometers, in fact. Not a chaotic mess, but a frozen graveyard. Some asteroids are big, monstrous, like Ceres, which is nearly 600 miles wide and even classified as a dwarf planet. Others, like Vesta or Pallas, are large enough to hold their own gravity. But most, they're the size of cars or refrigerators or pebbles. You could drift for days and never see one. They're not all doomsday devices. Some asteroids are made of metal, remnants of broken planetary cores. Others are just porous piles of rubble loosely held together by gravity. You could land on one and sink your boots into the dust. They don't burn with vengeance. They float, forgotten. But yes, the fear isn't entirely fiction. Earth has been struck before. 66 million years ago, one asteroid ended the age of the dinosaurs. It wasn't the size of Texas, more like 10 kilometers wide, but it hit with the force of billions of atomic bombs. Fires raged, skies darkened, ecosystems collapsed. And that wasn't the only one. Tunguska, Chelyabinsk, meteor crater in Arizona. Space throws stones more often than you'd like to admit. But not every asteroid is gunning for Earth. Most stay in their belt. Some are captured by Jupiter's immense gravity, circling like loyal satellites. Others pass near us, near, in the astronomical sense, millions of kilometers away, and we watch them. Constantly. Telescopes scan the sky, tracking near-Earth objects, NEOs, with obsessive precision. We map their orbits, calculate probabilities, imagine defenses. NASA's DART mission even slammed a probe into an asteroid just to see if we could nudge it, and we did. A cosmic billiard shot. Because fear isn't enough. We prepare. Not every rock is a death sentence. Some might bring answers. Asteroids carry the oldest material in the solar system. They contain clues to Earth's formation, even ingredients for life. Water, organic compounds, carbon, iron. Some scientists dream of mining them. You expected monsters. Instead, you found relics, silent, stony witnesses to the birth of everything. They're not villains. They're just leftovers. We can easily colonize Mars. You picture it easily. A glittering dome city beneath the red sky. Glass walkways, hydroponic gardens, astronauts in sleek suits gazing at twin moons rising over Martian hills. The headlines say, "We're going to Mars," It feels inevitable, like the next logical step, but then you step outside the fantasy and into the dirt. Mars is not friendly. It doesn't want us there. You're standing on a planet with no breathable air. The sky is dusty and thin. Temperatures plummet to minus 100 degrees Celsius at night. The sunlight is weak, only about 43% of what we get on Earth. And the radiation? Constant, unfiltered, pouring through the atmosphere that barely exists. You take one breath without your suit and your lung seize, you freeze, you die. Still want to colonize? Sure, we've sent rovers, drones, orbiters. We've mapped the terrain, studied the dust storms, even found water ice hiding beneath the surface. But building a city here? That's a different game entirely. First problem, getting there. A round trip to Mars takes 18 months to 3 years. There's no rescue if something goes wrong. No quick return flight. If your oxygen fails, or your food spoils, or your ship leaks, you're on your own. Then there's the logistics. You need habitats sealed against a vacuum. Machines to recycle air and water. Power sources that work in storms and sub-zero cold. Every meal has to be grown from scratch or shipped across 140 million miles. And the human body is not made for this. Muscles shrink in low gravity. Bones weaken. Radiation damages your cells, your DNA, your brain. Mars colonization isn't a weekend getaway, it's more like surgery with a rusted knife in a burning building. Heroic, but brutal. And yet, people still dream. SpaceX builds rockets. NASA draws blueprints. Engineers design inflatable habitats and lava tube shelters. Psychologists study isolation and long-term confinement. We're preparing, slowly, carefully, for a one-way trip into the unknown. Maybe someday we'll make it work. But don't expect glass domes and space golf anytime soon. Our first settlers, if they go, will live like Arctic researchers. Small crews, cramped stations, constant danger, years without a sunset that isn't filtered through red dust. There's no oxygen, no trees, no soft rain, just rock, ice, and endless horizon. To live here would be a triumph of science and a testament to suffering, because Mars is not Earth's twin. It's Earth's test. A day in space is always 24 hours. You open your eyes and check your watch. It says 7 a.m. Morning. The numbers are comforting, familiar. But then you glance out the window and you see Earth spinning below like a marble, and the sun rising. Again. For the second time in the last 90 minutes, time feels strange here. You're aboard the International Space Station, hurtling around the Earth at 28,000 kilometers per hour, one orbit every 90 minutes. That means 16 sunrises and 16 sunsets in a single Earth day. If you stuck your head at the window all day, you'd see the sky flip between black and orange-red over and over, like the world can't make up its mind. And yet, your schedule says it's just Monday. People think time in space works like time on Earth, that you still get 24 hours of day and night, that astronauts just follow some cosmic clock. But time up here isn't carved by shadows or marked by sunsets. It's invented, controlled, choreographed. You live by Coordinated Universal Time, UTC, the standard for space operations. NASA, ESA, Roscosmos, JAXA, all synchronized, not because that's what the sky tells you, but because otherwise your brain would fall apart. Imagine waking every 90 minutes to a new day. Your circadian rhythm would unravel. You'd stop knowing when to eat, when to sleep, when to work. Your body would revolt. Your mind would fray. That's why astronauts dim the lights and shut the blinds. They pretend time is stable, even when the sky says otherwise. And it's not just orbit. On the moon, a day lasts 29.5 Earth days. 2 weeks of blinding daylight, then 2 weeks of frigid night. Mars has it easier. A sol is about 24 hours and 39 minutes. close enough that rovers and future colonists might adjust without much friction. But out in deep space, heading for the outer planets, there are no sunrises, no time zones, no nightfall, just endless black. Time and space becomes a human invention, a tether to home. Without it, you drift. Not physically, but psychologically. Down on Earth, the ticking of a clock means something. Up here, it's just noise, like unless we agree it matters. So when people say, a day in space is 24 hours, they're both right and wrong. It's not about what space gives you, it's about what you bring with you, the hours, the rituals, the bedtime routines we use to stay sane. In space, we don't follow time. We build it. The vacuum of space is cold. You imagine it as freezing. The void. A dark, endless expanse of nothingness that bites at your skin the second you leave the ship. That's what they always say, right? Space is cold. But that's only half the story. See, cold means something different on Earth. It's about air temperature, how fast molecules are jiggling around you. In winter, those molecules move slowly. You lose heat to the air. Your skin tingles, your breath fogs. Cold is a transfer. Energy slipping from your warm body into something colder nearby. But space? There's nothing nearby. No air, no wind, no breeze to carry heat away. It's not cold in the way your skin understands. It's empty. And that changes everything. Imagine stepping into a room with no floor, no ceiling, no walls. Now remove the air, now remove the room. You're just a floating body surrounded by nothing but photons and particles zipping past like ghosts. In that void, heat can't leave you the usual way. There's no air to conduct it. No surface to touch and warm. The only way you lose energy is through radiation. Your body glows, ever so faintly in infrared, like a whisper of warmth bleeding off into the black. That's slow, unforgivingly slow. If you were in a spacesuit, floating in sunlight, you'd actually bake. There's no atmosphere to filter the sun's rays. Light hits you full force with no mercy. On the lit side of the moon, temperatures soar to 127 degrees Celsius, 260 degrees Fahrenheit. You could fry a steak on your helmet. But in the shadows, plunge a few feet into darkness, say behind a rock, and you're looking at minus 173 degrees Celsius, minus 280 degrees Fahrenheit. No warm breeze, no gentle chill, just a quiet drain of heat, radiated away like a secret. So space isn't cold like a freezer, it's indifferent. It doesn't steal warmth from you like a thief. It lets you lose it, slowly, invisibly on your own terms. Astronauts wear layers not just to stay warm, but to regulate. To stay balanced between two extremes, the searing light and the deathly dark. Satellites, too, have radiators and shields, shedding heat like medieval castles dumping waste out windows. Not because space is cold, but because space won't help you. It won't cool you down when you're hot. It won't warm you when you're cold. It just doesn't care. So next time you picture someone drifting through the void, don't imagine them shivering. Imagine them glowing, slowly bleeding warmth into a vacuum that never responds. Stars twinkle because they move. You lie back on a patch of grass, eyes pointed skyward. The night is clear, the stars are dancing, tiny pinpricks of light that shimmer, flash, and flicker like celestial fireflies. You've heard it all your life. Stars twinkle because they move. But that's not what's really happening. Not even close. Out there, in the vastness beyond Earth's veil, stars are stoic, steady. Cold-burning giants that don't dance, don't pulse, don't shift in little zigzags like playful spirits. Their light, when unbothered, is constant, piercing across light years without a hiccup. The twinkling? That's Earth's fault. Picture the star's light as a perfectly straight arrow fired across the galaxy. It flies undisturbed for trillions of miles until it hits the one place where chaos reigns. Your atmosphere. It's thick, uneven, alive. A boiling stew of shifting air currents, pockets of temperature, humidity, pressure, constantly roiling even on the clearest nights. When starlight enters this soup, it bends, warps, refracts. It's like looking through rippling water. The deeper you peer, the more the image distorts. The light that hits your eyes has taken a turbulent journey, jostled and jittered in the final sliver of its voyage. What was once a steady beam now flickers. It blurs, flashes red or blue, dances on your retina like a mirage. Not because the star moved, but because the sky did. That's why stars near the horizon twinkle more than those overhead. Their light has to cut through more atmosphere, more layers of wobbling, shifting air. It's like trying to see a candle through the waves of a swimming pool. And it's also why planets don't twinkle the same way. Planets are closer. Their light doesn't come from a single pinprick. It spreads out into a tiny disk. Those subtle variations in the atmosphere average out across the wider light source. The result? A steadier, calmer glow. Astronomers know this. That's why observatories sit on mountaintops to rise above the thickest, most turbulent layers of air. That's why we launched telescopes into orbit like Hubble and James Webb. Up there, beyond the blur of our sky, stars shine with perfect clarity. No twinkle, just fire. So when you see the stars dance tonight, remember, the performance isn't theirs. It's ours. The Earth, in all its beautiful chaos, is bending their ancient light into a glittering show. Not because the stars are restless, but because our sky can't keep still.